Well, good morning. It's great to be back. Every year I come here, privileged to be here. Strikes me how beautiful this campus is and how quiet, but until the lawnmower came. But I mean, it was just fantastic in these buildings. I say this because actually you're sitting in Berkeley right now. My God. And New Campbell Hall is not pretty. It is absolutely not pretty. It's functional, hopefully, but that's about all you can say. Okay, I would like to discuss with you two papers, one submitted and the other one in preparation, exploiting our integral field spectroscopy technique, mostly on the VLT, called SINS, and discuss two aspects, particularly for the very massive star-forming population on the main sequence. One is the discovery of a very frequent, high-duty cycle nuclear outflow phenomenon, and the second one is the first, what I believe is believable evidence for gravitational quenching. So this survey is based on initially a symphony-based surveying of the main sequence population in seeing limited mode. We by now have collected over last 7 years about more than 100 galaxies. We are now sort of done with that survey. You will see at the end that we are now just embarking on a next generation multiplexed by a factor of 20 called KMOS 3D. Likewise, of course, MOSFIRES will do similar things. But of these 110, we've now collected deep, really truly deep integral field spectroscopy assisted by AO. So that is typical resolution of 0.2 arc seconds, so 1.6 kiloparsecs for 35. That's a very large survey. In fact, the typical integration times we have collected for each and every one of them ranges between 5 and 20 hours. So the many galaxies we have with very deep integrations giving us exquisite spectra, and that's in fact what I will be using for these two projects. Now, more recently, we've also been able to get HST imagery, including with 3, so that we can get a handle at the stellar distribution. So here you see a summary, in fact, first of the H-alpha velocity fields in the stellar mass star formation rate plane, and you see, you know, the smaller, lower mass objects on the left, and then, of course, the bigger, more massive systems on the right. From the colors, you can see, in fact, that definitely for the more massive galaxies, rotation to first order is a very good description of the motions. As you go to the left, to the lower mass systems, that's less so, but as we've shown in a paper by Sarah Newman, to a significant extent, because at low masses and low resolution, you tend to smear out the rotational pattern, and in fact, when you do a better job, you can make a case that also for the lower mass galaxies, often called dispersion dominated, there's a fairly high fraction of rotation dominated systems. And in fact, the project I'll be describing first, second, will exclusively look at those objects which are rotationally dominated. And then you can go ahead from the HST imagery using pixel by pixels evolutionary modeling, which Stein-Reutz has been working on in our group, to also derive the stellar distribution. So what you're seeing here are not HST images, but actually the stellar images, and so the stellar surface density maps. And you can see that as you go from the the lower mass dispersion dominated sources on the left to the more big rotating disks on the right, at the same time you're also building up very substantial central stellar mass, and in fact the stellar images become fairly smooth. In a paper last year, Stein has made a very good case that in fact the clumps which we are all intrigued by in many of these bigger systems in fact are not typically also stellar maxima, but are star formation maxima of very young stellar populations. Now you may know that as part of this survey we've discovered evidence now on galaxy scales that most of these systems have outflows. As such, As such, that is not new. We know, of course, from the absorption work many people have been carrying out that outflows are common. But here we can study the occurrence of the outflows locally, map them out. In fact, also begin to measure mass outflow rates because we are dealing here with emission properties from hydrogen. So here you see one particular galaxy which shows that phenomenon. A ring system with very prominent clumps, and here you can see broad underlying components with rings out to plus minus 1,000 kilometers per second, which come from outflowing non-bound gas, and which you can assign to the individual clumps. But generally, in most of the main sequence population, at least above about 1 solar mass per year in kiloparsecs squared, you find these broad rings. They're extended across the galaxies and represent the base of the flows which you see in magnesium and the other absorption lines. So that's what you might want to call stellar feedback. But I don't want to talk about that now. I want to extend beyond this and tell you that we've discovered a second phenomenon. And that is when you step above about 10 to the 11, and you see there's this dotted cyan line here. There are in our survey 6, 7, 8 objects. All of these objects have outflows, as you will see, but these outflows are slightly different from the outflows which we see in the rest of the objects. And so what Natasha Förster-Schreiber, who is the first author of the paper, has done here is basically stuck in 2 dimensions. It's stuck in 2 dimensions after normalization of the scales, all of these galaxies. So here is integral field spectroscopy, so to speak, on a data set which has 200 hours integration. And so as you go inward in scale, which is which is given by this aperture you see there, you can see the spectra on the right exhibiting more and more of a broad component. Okay, let it go. You can see this broad component appearing clearer and clearer as you go in these galaxies. So then what we can do is we can either make images of the broad emission, and on the left side you see for these 6 galaxies, first of all the HST imagery, but then on the right, in the white contours, the distribution of that broad emission extracted from these H-alpha symphony data, and basically they are centered in the nuclei, and they're also slightly extended as we've seen in the, so this is not, so to speak, a point source, but it's about 1 to 2 kiloparsec in size. Now on the right, you see the stacked spectra. In blue, from the nuclei, and in the red from the disks. Now the disk emission, if you look closely, does show these broad components, which I argued before is the stellar feedback component. But as you will agree with me, I hope, is the nuclear components are much more powerful and broad distributions. Now the important point to make here is, as you look at this broad component, this is not a broad line component. So it's not what we would consider in local AGNs, this very compact parsec scale emission from broadline clouds. And that is because we see the broad emission from also the forbidden lines. We see it even in sulfur 2, we see it definitely in nitrogen 2, and it's spatially resolved. Now that means it comes on scales of a few kiloparsecs with full width half maximum, typically of 1,500 kilometers per second, so this cannot be bound material. So what we've discovered here is, in addition to the outflows we see throughout the disks, which in here as a function of mass, stellar mass, in red exists through all masses, including the high mass galaxies, there is a second component in blue which has high velocities, much higher than the stellar-driven outflows, and also nitrogen 2 over H alpha in the narrow component in the nucleus increases above 0.6, which is typically what you cannot explain anymore by photoionization. So you would put that in the BPD diagram in the domain of AGN. Now you would say, okay, so what? We know, in fact, from other evidence that the fraction of bona fide AGNs, as measured in X-rays, for instance, does increase with stellar mass, at least from a detection point of view. There's another question as what the underlying fractions are from a detection point of view, and that, you know, in the mass range above 10 to the 11, the fraction is about 20%. So is that just the 20% here we are observing? The answer is it doesn't seem to be, because we can take our sample as it is, eight galaxies, and 8 out of 8 show this. Not you know 2 out of 8, 8 out of 8. And we can go into the literature, and there's a number of people who've been taking nice spectra, not integral field spectroscopy, and certainly not adaptive optics integral field spectroscopy, but spectra, and you see the sample on the right, which you can compare to, and thereby enhancing the number of such objects to about 24. And then just looking at the spectra and making the same analysis we've done for our objects, you would say about 16 of those, including our own objects, show this phenomenon, so about 70%. So arguably, this outflow phenomenon is fairly frequent, and therefore it must be high duty cycle. And that's very interesting. I don't think anyone would doubt here that AGNs occur, and I don't think anyone would doubt that AGNs cause outflows. But the point here is we seem to be seeing a nuclear outflow phenomenon, probably triggered by AGNs, which has a high duty cycle. Now the estimates of the outflow rates are difficult and uncertain for sure, but they are high. The numbers we are estimating are somewhere between 60 and 1,100 solar masses per year. The outlook, I should say, in this field to really truly produce numbers rather than just qualitative impressions is very good, because we have the sulfur-2 line. And if you truly measure the sulfur-2 line ratio in high quality spectra, which undoubtedly we'll be able to do in the next years, in the broad component, then we have a density, and then you can use the recombination line emission measure directly to get mass outflow rates without any questions asked. But presently, I would say, despite the uncertainty, the numbers are high, and they are plausibly sufficient to do quite a damage to driving out gas in the nuclear regions. And because of the high duty cycle, that may be sort of a lasting phenomenon. So that's paper 1. Paper 2, in preparation, now takes the same sample, but not just the high mass galaxies, but now just restrict ourselves to those adaptive optic sets which are truly rotation dominated. The reason we want to do that is because we want to now measure the mass distributions very well in these galaxies, because what we are after here when we are looking at the issue of gravitational quenching is to measure the radial variation of the terminal Q parameter, and that requires us to measure the galactic shear. So what we've done here is to take 19 of the 35 galaxies which are rotation dominated. They are non-merger systems to the best extent we can. And so we can then model their velocity distributions, the intensity, velocities, and velocity dispersions as a function of radius with simple mass models. These mass models are non-unique, but that's not what we really need. What we need, as you look below, for the turmic parameter, we need the local velocity dispersion sigma naught. We assume it in this context that they are constant. And we need to measure the surface density of molecular gas sigma. And then we may have to measure kappa, which is the epicyclic frequency, which gives us the galactic shear. So the modeling of the mass distributions from the velocity data gives us kappa and sigma naught. And the inverse Kennecat-Schmidt relation, which Linda has just discussed, gives us sigma from H-alpha distributions modulo uncertain radial variations in extinction, which we cannot capture with this data, unfortunately, we have in front of us. So what do we find? On the left, we find that if you plot now the radial distribution of inferred molecular gas surface density distributions, and the different colors basically give you different masses. Blue and green are the lower mass half, and yellow and red are the higher mass half of the sample. Now, if you look at that, you sort of see the blue and some of the greens are sort of go down. So they're centrally peaked. But then, as you go to the yellow and red, they increase. H-alpha distribution is ring-like. Now, some of you have been discussing this matter with me in the past. I remember Avishai saying, you see these rings. I don't see any rings in my simulations. Most simulations don't see rings, actually. So what we knew, what Avishai knows, is that we've seen some rings. Now, I'm telling you, Avishai, of that sample, half of those are rings. And in fact, if you go to the more massive part, the massive half is even higher than that. Half of the distributions are rings. Now, of course, immediately, I cannot exclude at this point per se that the reason there's a dip in the center is due to extra extinctions which we cannot recognize. However, Stein-Voits has been using a larger sample from 3D HST. 3D HST is lower redshift, 0.5 to 1.7, but gives you H-alpha and stellar images at HST resolution, which is comparable here, although not as high a signal-noise ratio as what we have, so they have to do stacking of the imagery, and they do find, like what we find here, that the H-alpha to stellar equivalent width, which is extinction corrected, does show a central dip. Okay? So I'm arguing that these central dips largely, in fact, are an intrinsic phenomenon. Now, in the right picture, you see now derived Turner-Q distributions, the radial distribution Turner-Q. Again, the lower mass part is blue, and the upper mass part is red. And obviously, we would immediately see that there's a tendency for all of the galaxies to have larger Turner-Qs in their centers. That's not that surprising, and it's driven by the kappas, of course. The rotation curves for most of these galaxies are more flat than slowly rising. So that means that the epicyclic frequencies tend to rise to the center, which is the dominating phenomenon. But it's remarkable that for the upper mass half, the red ones, there are some which are clearly way above 1. So clearly those systems cannot be unstable to the gravitational fragmentation. So you can put this result into sort of a common summary slide. On the right, on the left side, again, the information on the molecular gas distributions. Look at the cyan plot. Basically, this is the ratio of the outer to the inner molecular gas ratios. And whenever this is above 1, then of course you would call that a ring. And then on the right side, you see the Q distributions. And in all galaxies, the outer Q distribution, the outer Q values in the disks, which are the red points in here, are way below 0. So that's the evidence, in fact, that these galaxies, as we've been arguing, are globally, or Avishai would say violently gravitationally unstable throughout their disks. But in the centers, that's not the case. That's not the case. They are indeed. And that would explain the rings. In fact, the fact that, our independent information from the rotation curves matches the imagery from H-alpha is non-trivial. Okay, is non-trivial and lends support to this interpretation that, yes, we are seeing an inside-out quenching of star formation in these disks. Now, the theorists amongst you have been talking about this for a while. I think here we have the first evidence. Now, the question is that due to the buildup of stellar mass in the centers? And so here we go to the HST work of ours, and now extract from that the central stellar surface densities, as well as the molecular surface densities. They typically are comparable, and plot them versus kappa. Because if kappa, the inner kappa, the one which drives the Qs above 1, in fact is driven by large central stellar buildup, then that should be seen. And here's the evidence. Looks pretty good, excepting 2 points. Those 2 points, one of the galaxies I've already shown, are these prominent big rings, which, however, in the stellar work, which we have. In both cases, we have stellar HST imagery, show no evidence for even extincted stellar peaks, at least not very prominent ones. So for most of the objects here which we can look at, indeed, the evidence here is consistent with the fact that indeed this quenching is due to the stellar buildup of a bulge, as you would say. But then there's two cases which are dark. Whether they are due to sterile gas, which just doesn't form stars, and therefore it doesn't show up in H-alpha. Or whether there is, very large extinction which cannot be even captured in the extinction, the SED mapping in the HST maps out to H-band is unclear to me. But I mean, this is real. This is not just a random excursion. Overall, however, I would say we do find evidence for this phenomenon, and I'm quite excited about it because it would give us a way to shut down those galaxies. And of course, there's probably only one of the modes, and couple now the gravitational quenching with the AGN feedback I talked before. We have two of the elements we've been talking about. Last slide, I just want to summarize our next plans. Linda already has discussed FIBS2. Very big effort. And likewise, we are now using KMOS, which we've been involved in building and led by Ray Sharpless, which is now on the telescope on the VLT, which offers 24 IFUs, although only in seeing limited mode, for very highly multiplexed observations. Commissioning is done very successfully. We have very good data sets already of about 60 galaxies, easy enough in a few nights to get good data sets, just like with MOSFire. Obviously, KMOS has the additional advantage of delivering velocity fields, which it does, although on seeing limited resolution. And so the outlook is bright that in about 2-3 years, both of these efforts, MOSFire and KMOS plus FIBS, will enhance all of what we've been talking about to a more robust level and sample somewhere between a few hundred to 1,000 galaxies. Thank you.
Thank Reinhard again. So if I understand correctly, what you would actually need to show to prove that it's a morphological quenching or gravitational quenching is you would also need to actually measure the gas there in the center and show that it's not just that there is an H-alpha ring because there's maybe just no gas in the center, right? So do you have some? I guess that with FIBS2 or maybe is there something?
Yes, obviously that's the path to go. And Robert, we would love to have done this already. The problem is that plateau is in the north, and symphony sins, and the rest of it happens in the south. Okay, so we don't have these beautiful rings which we can now go ahead and study with the plateau. But obviously this will be done, and I definitely would agree with you. We should be seeing molecular hydrogen and or of course H1, which we can't actually probe. Okay.
Very interesting that you're seeing evidence for a very high duty cycle in these greater than 10^11 solar mass galaxies. Do we also see, do you have either X-ray or infrared evidence that these objects have bright AGN?
So unfortunately, I again have to sort of waver on this, mainly because the fields here, Aegis is very shallow in X-rays. The Steidel fields are patchy, if anything. So the coverage of our symphony fields with X-rays is patchy at best. So of the 8 galaxies, I would say 1 or 2 show X-ray emission. One definitely what you would call a narrow line type 2 AGN, pretty powerful. The rest, in 1 or 2 cases, you could make the case that it's from the mid-infrared emission, that it's sort of a mid-infrared excess system. Some of the same galaxies, at least one, show AGN signatures in UV spectra. But it's not that, all these 8 immediately spring at you and produce AGNs. I would say the current set is not good enough to make statements about it. We have to be very careful now, and I mean, I would also suggest that to the MOSFire team to sort of assemble now these samples. Everyone will be looking at these kinds of issues, and then make sure we have a proper sampling of exactly that question to then answer, is that duty cycle higher than the AGN duty cycle? Yeah, that's the obvious question. I would suspect it might be, actually.
Which implies then what?
Well, that implies that the accretion at the event horizon is decoupled from the action of that AGN over slightly longer time scales, which doesn't surprise me at all. I mean, I don't know, you must have heard me say this. I strongly believe that black hole accretion is a local politics phenomenon, and it must be. And so, whatever you get to see on scales of 100 Schwarzschild radii may go up and down like crazy, yet the thing has been, producing these outflows, and they last. And you're looking here on a scale of kiloparsecs, right? So the dynamical time scales already are much larger.
Doesn't the cycle being so close to unity suggest that these outflows aren't actually damaging the galaxy that much? I mean, it must suggest that if every star-forming galaxy that's above a certain mass has outflows, then there's no star-forming galaxies that don't. So,
That's an interesting thought.
These can't be immediately shutting galaxies down.
Yeah, well, immediately I would say, yeah, right. Absolutely, I agree with immediately. Again, I would have thought actually, in terms of AGN feedback, how do they do this? Because of the famous phenomenon of shooting bullets through gas, right? I mean, so I would say this will take time, but it will help perhaps. That's I guess that's a very good question.
Okay, we run out of time, so